All right, today I'm talking about linear approximation, which is pretty much what it sounds like. We're going to use a tangent line to the graph of a function to approximate values of the function near the point of tangency. All right, so I'm just going to start with an example, the type of question you're going to see. Use the line tangent to the graph of f of x at x equals 1 to approximate f of 1.1 and f of 0.99. All right, well, I'm going to need to start by writing an equation for the line tangent to the graph of f at the point where x equals 1. Okay, so let's see, I'm going to need a point, and that'll be x is 1 and y is 1 to the third plus 3 times 1 is 4. The slope is going to be, well, that'll be f prime of 1. And the derivative of x to the third is 3 times x squared. Derivative of 3x squared is 6 times x. So when we plug in 1, we're going to get 9. Okay, now if we want to approximate the values of f of 1.1 and f of 0.9, we are going to be just plugging in 1.1 for x and 0.99 for x, and then approximating the value of y. So if I'm trying to approximate f of 1.1, I'm going to go over here and I'm going to say, well, y minus 4 is equal to 9 times x is 1.1 minus 1. And that's going to be 4 plus 9 times 0.1. And so I can say from there, that's going to be 4.9. I can say f of 1.1 is not equal to, but approximately equal to 4.9. Okay. I think it would be good for you to try this yourself. So I'm going to suggest that you do f of 0.99 on your own. If you're watching this video at home, you need to work this one yourself, but you should pause the video while you do it because the answer is just going to come up here in a few seconds. All right, there you go. So I did the same thing. Okay, I plugged in 0.99 for x, and then I started kind of solving it y. And I said that f of 0.99 was not equal to, but approximately equal to 3.91. All right. The other type of question they're going to ask you about linear approximation is, are we looking at an overestimate or an underestimate for the function, right? Now, what I'm going to do is I'm going to just draw what I'm going to suppose is the tangent line. And this is going to be an overestimate. Okay, so I want you to, on your own, draw a curve that this gray line is overestimating, right? The curve is going to have to sit below the tangent line. So, if you watched the last video or if you were sitting here in class last time, you know where this is headed, okay? But draw a curve that sits only below the tangent line. Okay, I'll do the same. What are we noticing about the curve in terms of its curvature? It's concave down, yes. Okay, so I'll say if f is concave down, linear approximations are overestimates, at least near the point of tangency, right? We don't know what happens. Maybe this thing has a change in concavity, and then all of a sudden the tangent line is not such a great estimator, right? But for values of x very close to the point of tangency, right, like, right there and right there, the tangent line's a pretty solid estimator. Okay. And then you might, already be expecting what would happen if the tangent line was an underestimate, but I'm going to, again, encourage you to think about what kind of curve would sit above this, and it's really going to be just a concave up curve. And again, just like I told you last time, or like with the second derivative test, I am really strongly recommending that you not try to just memorize this, right? That you instead internalize that it's the concavity that's causing something to be an overestimate or an underestimate. And then once you figure out the concavity, just draw a little picture, okay? Now, the picture can never be your reason, but it will help you get the right answer. And then we know that it's the concavity that's causing it, so we'll just say it's an overestimate because f of x is concave down at whatever the point of tangency is. Okay. Now, this is the type of problem that we really don't see anymore. But it is something we could use linear approximation for. Estimate the value of the square root of 26. Okay, was a time where you would have to look this up in a table of square roots, or maybe you would have to schedule time with a computer to calculate this before they came out with the 4-function calculator that also offered the square root function. That was a big thing. Okay, but we'll see, I'll show you that we can estimate the value of the square root of 26 pretty closely using a tangent line approximation. Well, I'll tell you right now, the function I should be using is square root x. What point should I use, though? What point on the graph of y equals square root x should I use? Square root of 25? Yeah, square root of 25. Because it's close to 26, right? If you think back to the first example we did, f of 1.1 and f of 0.99, f of 0.99, our approximation for that, is probably much closer to the true value than f of 1.1, or at least our estimation, because it's closer to the point of tangency. So you want to go as close to the point of tangency as you can with, some known value of the function. So I'm going to go and I'm going to say x equals 25 and, f of 25 equals 5. Now, f prime is going to be 1/2 x to the negative 1/2. So if I plug in 25, f prime of 25 is 1/2 of 1 over the square root of 25. Okay, so that's going to be 1/10. So the equation of the tangent line is y minus 5 equals 1/10 of x minus 25. And then I'm going to say, well, no, that's going to be 5 plus 1/10 of plug in 26. And this will be 5 plus 1/10, which is 5.1. All right, now, I also know what the graph of y equals square root x looks like, right? It's very concave down. So, is the true value of the square root of 26 going to be greater than or less than 5.1? Notice I asked that differently. I wasn't asking as an overestimate or an underestimate. Less than, yes. And if you're unsure, what do? You come in and you draw the little picture of the tangent line. Now, our approximation is, say, that. And then the true value is going to be right there on the purple curve. So, somebody has a calculator. Somebody's got to have a calculator here. It's close.
I got it.
It's close. I've got one. Oh, I've got one right here.
5.09.
Yeah. This is 5.09, but not just, that's what they told me yesterday. Oh, it's 5.09. That's great. If you go and plug this into the calculator, so it is certainly less than 5.1. It's 5.099. Okay, so we've got a really good approximator there. Okay, and that's a whole unit away. And so in some sense, this used to be, pretty powerful. Okay, the next example is, where they're going to give you information about a function and its first two derivatives, and they'll ask you to estimate the value of g of 4.9. Probably on a quiz or a test, it would say use the line tangent to the graph of g at the point where x equals 5 to approximate the value of g of 4.9. But that's kind of wordy. So let's say estimate the value of g of 4.9. We're just doing linear approximation today. And then I'm going to ask you if the approximation is greater than or less than the actual value of g of 4.9. Okay. I will warn you, this is the type of problem that could show up as in the data in the table incarnation. So why don't you try this one yourself? If you're working at home, you should try this one yourself as well. You're all ready to do this on your own. Okay. But if you're watching at home, you're going to want to pause the video because the answer is going to come up in just a few seconds. All right, there you go. So I started by writing the point and the slope and writing the equation, and then I plugged in 4.9. And eventually with the arithmetic, I found that g of 4.9 was approximately equal to 2.8. And since the second derivative was positive, I went ahead and drew a picture. Okay, I probably wouldn't, label the approximation versus the actual value if I was doing this myself, but I would still draw that little figure just to make sure. Remember, the approximation, it's a linear approximation. It sits on the line. The actual value is the one that sits on the curve. Okay. And regardless of if the point we're plugging in is less than the x value at tangency or greater than the x value at tangency, it's going to be the same result. Okay. So since I said because the graph of g is concave up, the approximation is less than the actual value of g of 4.9. There's probably a shorter way you could say that. But, that wasn't that long. Remember, the drawing is not proper justification. The explanation using the concavity of the function is. Next, we've got a good one. We've got one, which could be the value of f of 1.5 given multiple choices. So, they give us, same as kind of a previous problem, they give us information about f and its first two derivatives. And so, what I'm going to do is I'm going to use a linear approximation. Right? Well, that'll be y minus -1 equals 2 times x minus 1. We're interested in the actual value of f of 1.5, not the approximated value. Okay, but I'll start by approximating. F of 1.5 is approximately equal to -1 plus 2 times 1.5 minus 1. All right, so that's meaning that f of 1.5 is approximately equal to -1 plus 2 times a half is plus 1 is 0. Okay. Well, I know that because the second derivative is non-zero, the graph of f is not a line. So it can't equal 0. And knowing that f double prime is positive, that means that f is concave up. Say it's got slope 2, so I'll try to do it at a place where it has positive slope. But if, we approximate the function to be 0, the true value of the function has to be bigger than 0, right? So wouldn't want anybody to get fooled on that type of question, right? Because of the information about the second derivative, you know that it has to actually be greater than 0. Okay, here we have the first couple of parts of a free response question from 1998. Yeah, a function with f of 1 equals 4. That means that the point 1, 4 is going to be on the graph of f. And that for all points x, y on the graph, the slope is given by, the slope is given by, that means that this is dy dx. That's what dy dx means. This is the slope. So, find the slope of the graph of f at the point where x equals 1. Well, that'll be where x equals 1 and y equals 4. So I'll say dy dx at the point 1 and 4 is going to be 3 times 1 squared plus 1 over 2 times 4, which is going to be 4/8, or a half. Part B, write an equation for the line tangent to the graph at x equals 1. Well, I've got a point and a slope, so I'm ready to write an equation. Y minus 4 is 1/2 of x minus 1. Okay. See, this is the type of thing we could do. right now, if we were faced with this on the AP exam, we saw this on our free response, we could do this. We can write an equation for the line tangent to the graph at x equals 1 and use it to approximate f of 1.2. So we're going to plug in 1.2. Okay, so it's going to be half of 0.2 is 0.1. So let's say f of 1.2 is approximately equal to 4.1. I'll be happy. Now, I think part C was find f of x, basically, and you don't know how to do that yet. But, at our level right now, what part C would be find the second derivative of y with respect to x both times at the point where x is 1 and y is 4. Okay, we could do that. We could take the second derivative implicitly using the quotient rule. And then part D could be, is your estimate from part B an overestimate or an underestimate, right? We could do that. That would be something that you can safely expect to see on the homework and on the quiz next time. All right, now the last example I've got for you is one from 2015. And it says, consider the differential equation dy dx equals 2x minus y. Now, I think that part A on this one was likely a slope field, like something that y'all are going to really like in about, a couple weeks. We're going to, do some coloring, on a grid. It'll be great. Because this is not the type of differential equation that we're going to be able to solve in this course. But it's not going to ask us to actually find f of x. We're just going to do the max min neither thing, and then we're going to find the second derivative. Okay? So let's start with part B, the second derivative. I think this is implicit differentiation. We know how to do this. You know how to do this at home. I think you should do this yourself, right? And it says in terms of x and y, we can do this. And so you give it a shot, check your answer against mine. If you're watching at home, obviously you need to pause the video. You know the drill. All right, there you go. So the derivative of 2x with respect to x is 2, and the derivative of y with respect to x is dy dx. But they're saying they want it in terms of x and y, not in terms of x, y, and dy dx. So I've got this thing, and I just need to substitute 2x minus y. Now, as far as the concavity of solution curves for the differential equation in quadrant 2, what can we say about points in quadrant 2? Yeah, x is negative and y is positive, or y is positive and x is negative. Meaning that 2x minus y has got to be a negative number, right? So 2 minus a negative number has got to be positive. So what I'll say is, in, quadrant 2, x is negative and y is positive. Therefore, the second derivative is positive in quadrant 2. Meaning the curves are concave up, or something like that. Now part C. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 2 equals 3. So that means that the graph of f passes through the point x equals 2, y equals 3. Does f have a minimum, a maximum, or neither at x equals 2? So you should be thinking the same thing as, last time. We're going to have to use the second derivative test. We don't have any information about f besides it passes through the point 2, 3, and the slope is 2x minus y. Okay? So what we're going to do is we're going to make sure that the first derivative is 0, and then check the sign of the second derivative, right? Okay, so dy dx at the point 2, 3 is equal to 2 times 2 minus 3, which is 1. So what do I conclude? You're not going to be... Yeah, it's not going to be a minimum if the slope is 1. If the slope's positive, it's not going to be a maximum either. This is neither. And for justification, I think that's probably sufficient, but I might say neither, because dy dx at 2, 3 is non-zero. All right, I lied. I got another question for you. Here is, you're given the graph of a function, of a function's derivative, really, and they're going to tell you that h of 2 equals -1. Okay, write an equation for the line tangent to h at x equals 2. Well, that would be, point would be 2, -1. Slope is h prime of 2. Well, h prime of 2 is going to be the height of the graph right here, which is looking to me like 5. All right, and that would make the equation y plus 1 is 5 times x minus 2. All right, now maybe I would ask you about the linear approximation for h of 2.03. Well, I'm just going to plug in 2.03. So I would say it's approximately equal to -1 plus 5 times 2.03 minus 2 is 0.03. So that's -1 plus 15 cents would be -85 cents. Okay, so you could say it's about -0.85. Okay, if it's a free response situation, this would be a safe place to stop, right? We know that. Okay, now if they asked me if this was an overestimate or an underestimate, well, I'm going to say that since h prime is decreasing, h is concave down. So over here, it's only going to be a slight overestimate because it's so close to the point of tangency, but it is going to be an overestimate. I've got one more for you. All right, and this is not related to linear approximation, but I just still got to ask you, what's the value of h prime of 3? Anybody in here got any thoughts on the value of h prime of 3? The graph of h prime is shown. Yes, it's 2. Good for y'all. Y'all learned something last year. H double prime of 3, that fails to exist because of the sharp corner. Yes, good for you. Yeah, because the graph of h prime is shown, the derivative of h prime doesn't exist. H prime is not differentiable at x equals 3 because of the sharp corner. H prime of 3 does exist. It's 2. It's right there. That's all I got for you on this video.